Hi there, and welcome to my channel. My name is Matthew Gray. I'm so glad you found your way here tonight, because we're about to drift through the infinite quiet of the cosmos together. Wherever you are in the world right now, let this be your moment to release the day. Let the weight lift from your shoulders, the tension dissolve, and your mind become as vast and still as the space between stars. Tonight, we're venturing outward into the universe itself. The cosmos is more ancient, more gentle, and more breathtakingly harmonious than most of us ever pause to consider. From clouds of stardust that birth entire solar systems, to galaxies that dance in slow motion across billions of years, to the perfect mathematical rhythms that keep planets in their orbits, the universe moves with a grace that will soothe you, surprise you, and remind you of something profound. What you're about to hear isn't random. It's a journey through the hidden architecture of everything. The planets aren't scattered by chance. The stars don't burn without reason. Every element in your body, every breath you take, came from the heart of an ancient sun. We are all woven into this cosmic arrangement, this masterful design that has been unfolding for nearly 14 billion years. Some of what you hear tonight may quietly shift how you see the night sky. Other discoveries might simply wash over you like moonlight through a window, soft, curious, and gently unforgettable. If this peaceful sense of wonder brings you calm or sparks your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, settle in, get comfortable, take a deep breath, and let's begin this slow and soothing journey through the most relaxing truths about the cosmos. The universe is expanding, but not in the way you might imagine. Space itself is stretching, gently pulling galaxies apart from one another, like threads in a fabric that's being drawn wider with each passing moment. Rather than an explosion moving outward into empty space, the space between everything is simply growing larger, quietly, continuously, without any center or edge. Right now, as you rest here, galaxies millions of light years away are drifting farther from us. Not because they're racing through space, but because the space itself is expanding between us and them. The farther away a galaxy is, the faster expansion carries it away, not through any force or push, but simply because there's more space in between to stretch. Nearly 14 billion years have passed since the universe began, and expansion has continued throughout that entire span, and it will continue long after everything we know has faded into cosmic dust. And yet, nothing about it is violent or chaotic. It's smooth, measured, following laws so precise that we can predict exactly how fast any distant galaxy is moving away from us, just by knowing its distance. The gentle stretching of space reveals something even more calming about our cosmic home. Galaxies closest to us, the ones in our local neighborhood, aren't drifting away at all. Gravity holds them near, binding them together in what astronomers call the local group. Our Milky Way, the Andromeda Galaxy, and about 50 smaller galaxies all orbit one another in a slow cosmic dance that will last for billions of years. They're held together by invisible threads of gravitational attraction, each one tugging on the others in a balance so delicate and so stable that despite the universe expanding all around them, they remain close. In fact, Andromeda is actually moving toward us, not away. In about 4 billion years, these two great spiral galaxies will meet, their stars passing through one another like two clouds merging in a summer sky. Not a single star will collide. The distances between them are so vast that they'll simply drift past each other, eventually settling into a new, larger galaxy. It will be a merger, without violence, a cosmic reunion that unfolds over millions of years. Looking deeper into how galaxies move, we find that they don't travel alone through the expanding universe. They cluster together in groups, and those groups gather into even larger structures called superclusters, forming a vast web of matter that stretches across hundreds of millions of light years. Between these structures lie enormous voids, regions of space so empty that they contain almost no galaxies at all, just darkness and distance. The cosmic web, an architecture of matter and void, formed gradually over billions of years as gravity pulled matter together along invisible lines. The pattern looks almost biological, like the neural pathways in a brain or the root system of an enormous tree. And it's not random. Computer simulations that recreate the universe's history produce the exact same web-like pattern, proving that it emerged naturally from the simplest laws of physics. Gravity, acting patiently over vast spans of time, wove the universe into a delicate, lace-like form. Most of the universe is empty. When you look up at the night sky and see stars scattered across the darkness, you're actually looking at something incredibly rare. The vast majority of space contains nothing at all, not even a single atom. In fact, if you were to collect all the matter in the universe, every star, every planet, every particle of dust, and spread it evenly across all of space, you'd end up with roughly one hydrogen atom for every cubic meter. That's about the volume of a large refrigerator. One single atom. The rest would be pure vacuum, emptier than the emptiest laboratory chamber we've ever created on Earth. Rather than a flaw or a lack, emptiness is a feature. It's the canvas on which everything else exists, the silence between the notes that makes the music meaningful. And because space is so empty, light can travel for billions of years without hitting anything, carrying information about the early universe directly to our telescopes. Speaking of light traveling through emptiness, there's something almost magical about how we observe the universe. When you look at a star in the night sky, you're not seeing it as it is right now. You're seeing it as it was when the light left its surface, which might have been years, centuries, or even thousands of years ago. Light travels fast, about 186,000 miles per second, but the universe is so vast that even at incredible speed, light takes time to cross the distances between objects. The sun's light takes about 8 minutes to reach Earth, so when you watch a sunrise, you're seeing the sun as it looked 8 minutes earlier. The next closest star, Proxima Centauri, is about 4 light-years away, meaning the light you see from it tonight actually left that star 4 years ago. Some stars, visible to the naked eye, are hundreds or even thousands of light-years distant. When you gaze at them, you're looking backward through time, seeing the universe not as it is, but as it was. The night sky is a time machine, showing us the past in every direction. Looking backward through time becomes even more profound when we observe the most distant objects in the universe. The farthest galaxies we've observed are so remote that their light has been traveling toward us for over 13 billion years, meaning we're seeing them as they appeared when the universe itself was less than 1 billion years old. These ancient galaxies look different from the ones nearby. They're smaller, more irregular, filled with young stars burning hot and blue. They're cosmic children, galaxies in the process of forming, still gathering mass and taking shape. By now, in their present moment, they've likely grown into massive spiral or elliptical galaxies, perhaps with their own planets, their own suns, maybe even their own civilizations, looking back at us across the same impossible distance. But we'll never see them as they are now. The light showing us their current state won't reach Earth for billions more years. We're forever separated from them, not just by distance, but by time itself. Understanding how light travels helps us grasp something even more calming about the cosmos. Despite its vastness, despite the incomprehensible distances and timescales, the universe follows rules. Light always travels at the same speed through empty space, no matter where you are or how fast you're moving. Constancy, reliability, these form one of the foundations of physics. It means that the laws governing the universe here on Earth are the same laws operating in the farthest reaches of space. Gravity works the same way everywhere. Atoms behave identically in distant galaxies as they do in laboratories. Stars form through the same processes, whether they're in our Milky Way or in a galaxy 10 billion light-years away. Universal consistency means we can understand the cosmos. We can predict how stars will evolve, how planets will form, how galaxies will interact. The universe isn't chaotic or arbitrary. It's orderly, predictable, governed by principles that remain constant across all of space and time. Order extends to one of the most beautiful phenomena in the night sky, the gradual evolution of stars. Stars don't last forever, but they don't vanish suddenly either. They live through stages, each one lasting millions or billions of years, following a predictable path determined by their mass. Our Sun, a medium-sized star, has been shining steadily for about 4.5 billion years, and it will continue burning hydrogen in its core for another 5 billion years before anything changes. When its fuel begins to run low, it will swell into a red giant, its outer layers expanding until they reach beyond Earth's current orbit. Transformation won't happen overnight. It will unfold gradually over hundreds of millions of years, giving any civilizations in the galaxy plenty of time to see it coming. Eventually, it will shed those outer layers into space, creating a glowing shell of gas called a planetary nebula, while its core collapses into a white dwarf, a dense ember that will cool slowly over trillions of years. Nothing about the process is violent or sudden. It's simply the natural conclusion of a star's life cycle, as gentle and inevitable as autumn giving way to winter. White dwarfs, the remnants of stars like our Sun, have a strange and calming quality all their own. They're incredibly dense, packing roughly the mass of the Sun into an object about the size of Earth. A teaspoon of white dwarf material would weigh several tons. Yet, despite density, they pose no danger to anything around them. They simply sit in space, cooling gradually, radiating away their stored heat over unimaginable spans of time. A white dwarf takes trillions of years to cool completely, far longer than the current age of the universe. In fact, the universe isn't old enough yet for any white dwarf to have cooled all the way down to a theoretical black dwarf, a cold, dark cinder that no longer emits any light. Every white dwarf that exists today is still glowing faintly, still warm from the fusion reactions that powered it billions of years ago. They're cosmic embers, marking the final resting places of ancient stars, drifting quietly through the galaxy as they slowly fade into darkness. Not all stars end their lives so peacefully. Massive stars, those much larger than our Sun, experience a different fate entirely. When they exhaust their fuel, they don't simply cool and fade. Instead, their cores collapse in a fraction of a second, triggering an explosion so powerful that for a brief time, a single star can outshine an entire galaxy. These events, called supernovae, are among the most energetic phenomena in the universe. Yet even in their violence, there's a kind of order and purpose. Supernovae don't just destroy, they create. The explosion forges heavy elements like gold, silver, and uranium, elements that can't form inside normal stars. These newly created atoms are blasted into space, mixing with clouds of gas and dust that will eventually collapse to form new stars and planets. Every atom of gold in a wedding ring, every atom of iron in your blood, was created inside a dying star and scattered through space by a supernova billions of years ago. We are, quite literally, made of stardust, the remnants of ancient explosions that enriched the galaxy with the building blocks of planets and life. Cycles of stellar birth and death reveal something profound about the universe's patience. The elements necessary for life didn't exist in the beginning. When the universe first formed, only hydrogen and helium existed, the two simplest elements. Everything else, every atom of carbon in your body, every atom of oxygen in the air you breathe, had to be created inside stars over billions of years. The first generation of stars formed from pure hydrogen and helium, burned through their fuel, and exploded as supernova, seeding space with heavier elements. A second generation formed from enriched material, lived their lives, and added even more elements to the mix. Our Sun is at least a third generation star, formed from gas clouds that had been enriched by multiple cycles of stellar death and rebirth. The iron in Earth's core, the silicon in its crust, the calcium in your bones, all of it took billions of years and countless stellar generations to create. The universe worked patiently, star by star, explosion by explosion, to build the periodic table from the ground up. Gradual enrichment of the cosmos with heavy elements leads us to consider how planets form in the first place. They emerge from the same clouds that birth stars, vast regions of gas and dust called nebulae. When a cloud begins to collapse under its own gravity, most of the material falls toward the center, where it eventually ignites to become a star. But not everything makes it to the center. Some material remains in orbit, forming a flat disk around the young star. Within that disk, dust grains collide and stick together, gradually building up into larger and larger clumps. These clumps attract more material through their own gravity, growing into objects called planetesimals, which are essentially the seeds of planets. Over millions of years, planetesimals collide and merge, eventually forming full-sized planets. The entire process, from dust grain to planet, takes about 10 to 100 million years. It's not fast by human standards, but in cosmic terms, it's remarkably quick, and it happens naturally, automatically, whenever a star forms, which means planets are likely common throughout the universe. Thinking about how common planets might be brings a sense of companionship to our place in the cosmos. For most of human history, we didn't know if other planets existed beyond our solar system. We could see our neighboring worlds, but we had no way to detect planets orbiting distant stars. That changed in the 1990s when astronomers developed techniques sensitive enough to find them. Since then, we've discovered thousands of exoplanets, planets circling other stars. They come in an astonishing variety. Some are gas giants larger than Jupiter. Others are rocky worlds smaller than Earth. Some orbit so close to their stars that their surfaces are molten. Others drift so far away that they're frozen solid. Many exist in multi-planet systems, with several worlds orbiting the same sun. Based on what we've found so far, astronomers estimate that nearly every star in the galaxy has at least one planet. That means there are hundreds of billions of planets in the Milky Way alone, a population so vast it's almost impossible to comprehend. We are not unique. Worlds are everywhere. Among those hundreds of billions of planets, some must reside in what astronomers call the habitable zone, the region around a star where conditions are just right for liquid water to exist on a planet's surface. Water is essential for life as we know it, so finding planets in zones like these is one of the main goals of exoplanet research. The habitable zone isn't a single distance. It depends on the star's size and temperature. Around a small, cool star, the habitable zone lies much closer than it does around a large, hot star. Earth sits comfortably within the Sun's habitable zone, receiving just enough warmth to keep oceans liquid without boiling them away. Several discovered exoplanets also orbit within their stars' habitable zones. They're the right distance from their suns to potentially host liquid water, and by extension, perhaps life. We don't yet know if any of them actually have water, let alone life, but the possibility exists. The universe has provided the right conditions in many places. Whether life arose to take advantage of those conditions is a question we're only beginning to explore. Considering the possibility of life elsewhere in the universe brings a gentle reassurance rather than anxiety. If life exists beyond Earth, it likely developed through the same basic chemistry that governs life here. The elements necessary for biology, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are common throughout the cosmos. The laws of chemistry work the same way everywhere. Amino acids, the building blocks of proteins, have been found in meteorites and detected in interstellar space. The ingredients for life aren't rare or exotic. They're ordinary, scattered throughout the galaxy. What remains uncertain is whether those ingredients actually assembled into living organisms elsewhere. Life might be common, arising wherever conditions permit. Or it might be rare, requiring not just the right chemistry, but also the right circumstances, the right timing, perhaps even a bit of luck. Either answer is profound. If we're alone, it makes Earth and everything on it extraordinarily precious. If we're not alone, it connects us to a larger community, a universe teeming with biology. Both possibilities inspire wonder rather than fear. Whether or not life exists elsewhere, our own existence here on Earth required an extraordinary sequence of events. The planet formed at just the right distance from the Sun. It grew large enough to hold an atmosphere, but not so large that it became a gas giant. It developed a magnetic field that shields the surface from harmful solar radiation. It has a large moon that stabilizes its axial tilt, preventing wild swings in climate. Water arrived, possibly delivered by comets and asteroids, early in the planet's history. A breathable atmosphere developed gradually over billions of years as photosynthetic organisms released oxygen. None of these things were guaranteed. They happened through a combination of natural processes and, in some cases, fortunate accidents. The Moon, for instance, likely formed when a Mars-sized object collided with the young Earth, blasting debris into orbit that eventually coalesced. Without that collision, Earth might not have a moon at all, and without the Moon, life might have developed very differently, if at all. We're here because of a long chain of events, each one building on the last. A long chain of events unfolded over timescales that are almost impossible to grasp. Earth formed about 4.5 billion years ago from the same disk of material that gave birth to the Sun. For its first few hundred million years, it was a hellish place, bombarded constantly by asteroids and comets, its surface covered in molten rock. Gradually, as the bombardment slowed, the planet cooled enough for water vapor in the atmosphere to condense and fall as rain. Rain continued for millions of years, filling the first oceans. Life appeared remarkably quickly after that, with the earliest evidence of simple single-celled organisms dating back to about 3.5 billion years ago. These first life forms were nothing like the complex creatures we see today. They were bacteria, microscopic organisms that survived in extreme environments, feeding on chemicals rather than sunlight. But they were alive, capable of reproducing and evolving. Everything that exists today, every plant, every animal, every fungus, descended from those ancient bacteria. Life took hold early on Earth and has persisted ever since, adapting to every change the planet threw at it. Life's persistence through billions of years speaks to its resilience, but also to the stability of Earth's environment. The planet has remained habitable for an extraordinarily long time, maintaining liquid water on its surface despite significant changes in the Sun's brightness. When life first appeared, the Sun was about 30% dimmer than it is today. You'd expect that a dimmer Sun would make Earth colder, possibly freezing the oceans solid. Yet life thrived. The planet stayed warm because its atmosphere contained much higher levels of greenhouse gases, particularly carbon dioxide, which trapped heat and compensated for the Sun's weakness. As the Sun gradually brightened over billions of years, life itself modified the atmosphere, removing carbon dioxide and adding oxygen. The process, driven by photosynthetic organisms, prevented the planet from overheating. It's a remarkable feedback system. Life changed the atmosphere in ways that kept Earth habitable, even as external conditions shifted. The planet and its inhabitants co-evolved, each shaping the other. Co-evolution between life and environment is part of a broader balance that characterizes Earth's climate system. The planet has natural mechanisms for regulating its temperature over long timescales. When the atmosphere gets too warm, increased rainfall weathers rocks faster, which pulls carbon dioxide out of the air and stores it in the form of carbonate minerals. When the atmosphere cools too much, volcanic activity releases stored carbon dioxide back into the air, warming things up again. The cycle, called the carbon silicate cycle, operates over hundreds of thousands to millions of years, acting as a planetary thermostat. It's not perfect, and it doesn't prevent shorter-term fluctuations, but it has kept Earth's temperature within the range necessary for liquid water for billions of years. Even during ice ages, when large portions of the planet were covered in glaciers, the oceans never froze completely. Even during warmer periods, when Earth had no ice caps at all, the oceans never boiled away. The planet stays within bounds, regulated by natural processes that have operated since the oceans first formed. Natural regulatory systems extend beyond just temperature. Earth's magnetic field, generated by the motion of molten iron in the planet's outer core, creates a protective bubble around the planet called the magnetosphere. An invisible shield deflects most of the charged particles streaming from the sun in the form of the solar wind. Without it, those particles would strip away the atmosphere over time, the way they did on Mars after its magnetic field shut down billions of years ago. Earth's magnetosphere has been operating continuously for at least 3.5 billion years, possibly longer. It's not constant in strength. The field weakens occasionally, and every few 100,000 years, the magnetic poles flip, with north becoming south, and south becoming north. During these reversals, the field weakens significantly, but never disappears entirely. Even in its weakest state, it still provides some protection. And despite numerous reversals throughout Earth's history, life has continued uninterrupted. The shield bends, but never breaks, keeping the atmosphere intact and allowing life to persist beneath it. Looking beyond Earth's protective bubble, we find that our planet isn't the only place in the solar system with interesting features. Jupiter, the largest planet, has a fascinating role in the structure and stability of our cosmic neighborhood. Its immense gravity acts like a cosmic vacuum cleaner, attracting and capturing asteroids and comets that might otherwise wander into the inner solar system. Many objects that could potentially collide with Earth instead get pulled into Jupiter's gravitational field, either crashing into the planet or being flung out of the solar system entirely. Some scientists believe Jupiter's presence has reduced the frequency of major impacts on Earth, giving life more time to develop, without being repeatedly wiped out by catastrophic collisions. It's not a perfect shield. Some objects still get through, but Jupiter's gravity subtly alters the trajectories of countless small bodies, redirecting them away from the inner planets. It sits out there, a giant guardian, quietly shaping the paths of debris throughout the solar system. Jupiter's influence extends to its own system of moons as well, a miniature solar system orbiting the giant planet. 4 of these moons are large enough to see with binoculars from Earth. They're called the Galilean moons, after Galileo, who first observed them in 1610. Each one is a world unto itself. Io, the innermost, is the most volcanically active body in the entire solar system, its surface constantly reshaped by eruptions driven by tidal forces from Jupiter's gravity. Europa, the next moon out, has a smooth ice surface that likely covers a deep ocean of liquid water beneath. Ganymede, the third moon, is the largest moon in the solar system, even bigger than the planet Mercury, and it also probably has a subsurface ocean. Callisto, the outermost of the 4, is ancient and heavily cratered, its surface preserving a record of impacts dating back billions of years. These moons orbit Jupiter in a precise resonance, their periods related by simple mathematical ratios that keep their orbits stable over vast stretches of time. Orbital resonance among Jupiter's moons demonstrates another example of the universe's underlying order. Resonances occur when 2 or more orbiting bodies exert regular, periodic gravitational influences on each other. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. Precision like that isn't coincidental. It emerged naturally as the moons migrated through Jupiter's gravity field early in the solar system's history. The resonance locks them into a configuration that remains stable over billions of years. Similar resonances exist throughout the solar system. Neptune and Pluto are in a resonance, as are several asteroids and Jupiter. Even some exoplanet systems show resonant patterns, suggesting it's a natural outcome of how planets and moons interact gravitationally over time. The universe arranges itself into these elegant patterns not through conscious design, but simply through the patient working of gravity. Beyond Jupiter lie the outer planets, Saturn, Uranus, and Neptune, each contributing to the solar system's architecture in its own way. Saturn, famous for its rings, sits nearly twice as far from the Sun as Jupiter. Its rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders, all orbiting the planet in a flat disk. The rings aren't solid. They're more like a swarm, each particle following its own orbit, jostling and colliding with its neighbours. Despite their grand appearance, the rings are surprisingly thin, in most places only about 30 feet thick. They're also relatively young, perhaps only a few 100 million years old, formed when a moon or comet ventured too close to Saturn and was torn apart by tidal forces. Eventually, the rings will disappear, pulled down into Saturn's atmosphere by drag, and scattered by gravitational interactions with the planet's moons. For now, though, they circle the planet in graceful loops, a temporary ornament on a world that will exist for billions more years. Farther out, Uranus and Neptune orbit in near darkness, so distant from the Sun that they receive only a fraction of the light and warmth Earth enjoys. Both are ice giants, made mostly of water, methane, and ammonia, surrounding a rocky core. They have atmospheres of hydrogen and helium, but lacked the massive quantities of these gases that characterize Jupiter and Saturn. Uranus has an unusual tilt. Its axis of rotation lies almost in the plane of its orbit, meaning it essentially rolls around the Sun like a ball rather than spinning like a top. An extreme tilt like that likely resulted from a collision with another large object early in the solar system's history, an impact violent enough to knock the entire planet onto its side. Despite odd orientation, Uranus maintains a stable orbit, circling the Sun once every 84 years. Neptune, the farthest known planet, takes 165 years to complete a single orbit. It has the strongest winds in the solar system, with storms that rage at speeds exceeding 1,000 miles per hour. Yet even these fierce winds follow predictable patterns, driven by the planet's internal heat and its rapid rotation. Out beyond Neptune's orbit lies a vast region called the Kuiper Belt, a disc-shaped zone filled with icy bodies left over from the solar system's formation. These objects, sometimes called Kuiper Belt objects or trans-Neptunian objects, are remnants of the material that built the outer planets. There are likely hundreds of thousands of them, larger than 60 miles across, and billions of smaller ones. Pluto, once considered the 9th planet, is one of the larger members of the population. It shares the Kuiper Belt with similar-sized objects like Eris, Haumea, and Makemake. These distant worlds orbit slowly in the cold and dark, taking centuries to circle the Sun. Some have eccentric orbits that carry them closer to the Sun at times, while others follow nearly circular paths. They're cold, dark, and silent, but they're not dead. Some may have subsurface oceans kept liquid by internal heat. Others might have atmospheres that freeze and fall as snow when they're far from the sun, then evaporate again as they swing closer. Even in the outer reaches of the solar system, worlds continue their slow, patient journeys through space. Beyond the Kuiper Belt, even farther from the sun, lies a hypothetical region called the Oort cloud, a vast spherical shell of icy objects surrounding the entire solar system. Unlike the Kuiper Belt, which is a disk, the Oort cloud is thought to be roughly spherical, extending outward in all directions. It begins somewhere beyond the orbit of Neptune and stretches perhaps halfway to the nearest star, a distance of 1 or 2 light years. Distance like that means objects in the Oort cloud are barely bound to the sun by gravity. A passing star could disturb their orbits, sending some plunging toward the inner solar system, where they become visible as comets. In fact, most long-period comets, those that take thousands or even millions of years to orbit the sun, are believed to originate from the Oort cloud. These objects have been drifting out there since the solar system formed, frozen relics from the very beginning. We've never directly observed the Oort cloud because its members are too small and too far away to see. But its existence explains where comets come from, and reminds us that the sun's influence extends much farther than the visible planets. Comets themselves are fascinating objects, often called dirty snowballs, because they're made of ice mixed with dust and rock. They spend most of their lives in the cold outer reaches of the solar system, completely frozen and inactive. But when a comet's orbit brings it close to the sun, the ice begins to vaporize, releasing gas and dust that form a glowing atmosphere called a coma around the nucleus. Solar wind and radiation pressure push material away from the sun, creating 2 tails, one made of gas and one made of dust, both pointing away from the sun regardless of the comet's direction of travel. These tails can stretch for millions of miles, making comets among the largest objects in the solar system, even though their solid nuclei are typically only a few miles across. A comet's display is temporary. After passing the sun, it retreats back into the outer solar system, its ice refreezing, its tails disappearing, leaving only the small, dark nucleus continuing its long, lonely orbit. The dust that comets leave behind as they orbit doesn't just vanish. It spreads out along the comet's path, forming a trail that Earth occasionally passes through. When it happens, particles of cometary dust enter our atmosphere at high speed, burning up and creating what we call meteor showers. These events occur at predictable times each year because Earth crosses the same cometary paths at the same points in its orbit. The Perseids in August, the Geminids in December, and the Leonids in November are all caused by Earth passing through debris left behind by specific comets. Each meteor you see during a shower is a tiny piece of ancient ice and rock, a fragment that has been drifting through space for thousands or millions of years, finally meeting its end in a brief flash of light high above the ground. There's something poetic about it. Material that once floated in the frozen darkness of the outer solar system ends its journey in a moment of brilliance, burning away to nothing as it falls through our sky. Meteor showers are entirely harmless. The particles are typically no larger than a grain of sand, and they burn up completely at altitudes of 50 to 75 miles, far above where aircraft fly. They pose no danger to anything on the ground. Even larger meteors, those that produce bright fireballs and occasionally survive the journey through the atmosphere to land as meteorites, are rare and rarely cause damage. Most of Earth's surface is ocean or uninhabited land, so even when a meteorite reaches the ground, it usually lands somewhere remote. The few that have been found and studied provide valuable information about the solar system's composition and history. Some meteorites are fragments of asteroids that have been drifting through space since the beginning. Others are pieces of the Moon or even Mars, blasted into space by ancient impacts and eventually swept up by Earth's gravity. Holding a meteorite is like holding a piece of the early solar system, a sample of material that formed 4.5 billion years ago and has remained largely unchanged since then. Asteroids, the parent bodies of most meteorites, are scattered throughout the solar system, but concentrate mainly in a region between Mars and Jupiter called the asteroid belt. The belt contains millions of rocky objects, ranging in size from tiny pebbles to bodies hundreds of miles across. Despite popular depictions in science fiction, the asteroid belt is not densely packed. The average distance between asteroids is so vast that a spacecraft could pass through the belt without coming anywhere near one. In fact, multiple spacecraft have already done exactly that, passing through the belt without incident on their way to the outer solar system. The total mass of all asteroids combined is less than 5% of the Moon's mass, nowhere near enough to form a planet. These are simply the building blocks that never assembled, leftover material from the solar system's formation that remained scattered instead of coalescing into a larger world. Many asteroids follow stable orbits that have changed little over billions of years. They circle the Sun in the same paths their fragments have followed since shortly after the solar system formed. Jupiter's powerful gravity prevents them from clumping together into a planet, stirring their orbits and causing collisions that fragment larger asteroids into smaller pieces. Over time, collisions have ground down what might once have been fewer, larger bodies into the swarm of smaller objects we see today. Yet, despite all the grinding, asteroids remain, orbiting patiently in their assigned region of space. Some are solid rocky bodies, dense and undifferentiated. Others are rubble piles, loose collections of fragments held together by their own weak gravity. A few are metal-rich, likely the exposed cores of larger objects that were shattered by ancient impacts. Each one carries information about conditions in the early solar system, preserved in its composition and structure. Some asteroids don't stay in the main belt. Their orbits, perturbed by gravitational interactions with Jupiter or collisions with other asteroids, shift over time. A few drift inward, crossing the orbits of Mars, Earth, Venus, or even Mercury. These are called near-Earth asteroids, and we keep close watch on them because there's a small but real chance one could eventually collide with our planet. Before you worry, understand that space is vast and asteroids are small. The likelihood of a significant impact during any human lifetime is extremely low. Astronomers have catalogued most of the large near-Earth asteroids, those big enough to cause global effects if they hit, and none have orbits that will bring them dangerously close to Earth anytime soon. Smaller asteroids hit more often, but they typically explode in the atmosphere without causing damage on the ground. The universe isn't targeting us. Collisions are just a natural part of having rocky bodies orbiting the same star. Even when impacts do occur, they're part of the natural process that shaped our planet. Earth has been struck by asteroids and comets countless times throughout its history. Large impacts are rare on human timescales, but common over geological time. The famous impact that contributed to the extinction of the dinosaurs 66 million years ago was caused by an object only about 6 miles across. The crater it left, buried beneath sediment on the Yucatan Peninsula, measures over 100 miles in diameter. That impact released energy equivalent to billions of nuclear weapons, triggering earthquakes, tsunamis, and a global winter that lasted for years. Yet life survived. Many species went extinct, but many others endured. Within a few million years, new species had evolved to fill the empty ecological niches. The planet recovered, as it always has. Impacts don't end life on Earth. They reshape it, create opportunities for new forms to emerge, and remind us that change, even catastrophic change, is part of the natural order. Looking beyond our solar system again, we find that planets around other stars likely experience similar impacts. Young planetary systems, like ours was billions of years ago, are especially chaotic, with countless rocky and icy bodies crossing paths and colliding. Over time, the largest objects clear out their neighborhoods, either by accreting smaller bodies or by flinging them into different orbits. Eventually, the system settles into a more stable configuration, with planets following regular orbits, and most of the leftover debris either swept up or pushed into distant reservoirs. The process, called dynamical clearing, is thought to be universal. Every planetary system goes through it. Some systems might settle faster than others, depending on the masses and positions of their planets. But eventually, they all reach a state of relative calm where major collisions become rare. If exoplanets follow patterns like these, then many of them likely reside in stable systems where conditions have remained relatively constant for billions of years. Plenty of time for life to emerge and evolve if the right conditions exist. Stability in planetary systems depends heavily on the spacing between planets. If planets orbit too close to one another, their gravitational interactions become chaotic, potentially leading to collisions or ejections. If they're spaced far enough apart, however, their orbits remain stable indefinitely. Astronomers have found that many exoplanet systems show signs of past instability. Some have planets with highly eccentric orbits, suggesting they were once part of systems with more planets that interacted gravitationally and scattered each other. Other systems have planets that seem too massive to have formed where they currently orbit, implying they migrated inward from farther out. Our own solar system appears to have gone through a period of migration early in its history. Jupiter and Saturn may have moved inward, then outward again, a dance that stirred up the asteroid belt and sent a shower of comets toward the inner planets. Migration happened billions of years ago, and since then, the system has settled into its current stable configuration. The planets orbit today much as they have for the last 4 billion years. Long-term stability allows us to predict planetary motions with extraordinary precision. We can calculate where Mars will be in the sky 10 years from now, down to the second. We can predict eclipses centuries in advance. We can determine when Venus will transit across the face of the Sun, an event that occurs in pairs separated by 8 years, with each pair separated by more than a century. Predictability like that isn't magic. It's simply the result of gravity acting on objects following well-defined orbits. The math involved, developed by scientists like Isaac Newton and Johannes Kepler centuries ago, describes how objects move under the influence of gravity. These equations work just as well for moons orbiting Jupiter as they do for galaxies orbiting each other. They apply to everything, everywhere, making the universe understandable. And because they apply everywhere, we can look at distant exoplanets and predict their climates, estimate their temperatures, guess at whether they might have seasons. The laws governing their behavior are the same laws governing Earth. Seasons themselves are a beautiful consequence of orbital mechanics. Earth's axis tilts about 23.5 degrees relative to the plane of its orbit. As the planet moves around the Sun, tilting causes different hemispheres to receive more or less direct sunlight at different times of year. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere, tilted away, experiences winter. 6 months later, the situation reverses. The tilt remains constant throughout Earth's orbit, always pointing in the same direction in space. But because the planet moves, the angle at which sunlight strikes each hemisphere changes. A simple geometric relationship like that creates the seasons we experience every year. It's not complicated. It's just a planet tilting as it orbits a star. Yet tilting has profound effects on climate, weather patterns, and the distribution of life across the planet's surface. Other planets experience seasons too, though not always like Earth's. Mars has a similar axial tilt to Earth, about 25 degrees, so it has seasons comparable to ours, though they last nearly twice as long, because Mars takes longer to orbit the Sun. Jupiter's tilt is only about 3 degrees, so it has almost no seasons at all. Uranus, tilted at 98 degrees, has the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of total darkness. Imagine living through a summer that lasts for decades, followed by a winter just as long. Extreme variations like that would create bizarre weather patterns and climate zones, unlike anything on Earth. Yet even Uranus's orbit is stable, its tilt unchanging. The planet continues its slow roll around the Sun, its seasons unfolding over spans of time longer than human lifetimes. The predictability of orbital patterns extends beyond individual planets to the entire solar system's motion through the galaxy. Our Sun isn't stationary. It orbits the center of the Milky Way, just as planets orbit the Sun. The orbit takes about 225 to 250 million years to complete, a span of time sometimes called a galactic year. The Sun has completed the journey roughly 20 times since it formed. Right now, it's moving through the galaxy at about 500,000 miles per hour, carrying the entire solar system along with it. All the planets, asteroids, comets, and everything else bound to the Sun by gravity travel together, maintaining their orbits around the Sun even as the Sun itself follows its vast orbital path through the galaxy. From a galactic perspective, the solar system is just one small structure circling the Milky Way's center, along with hundreds of billions of other stars. The center of the Milky Way is a fascinating place, though we can't see it directly in visible light, because thick clouds of dust block our view. Radio waves and infrared light can penetrate the dust, however, revealing a dense cluster of stars surrounding a supermassive black hole. The black hole contains about 4 million times the mass of the Sun, compressed into a region smaller than our solar system. Despite its enormous mass, it poses no threat to Earth, or even to stars orbiting nearby. Black holes are dangerous only if you get extremely close, within a few times their radius. Beyond that distance, their gravity behaves like that of any other object with the same mass. Stars orbit the galactic center, following the same gravitational laws that govern planetary orbits. Some pass very close to the black hole, completing their orbits in just over 10 years. Observations of these stars have allowed astronomers to measure the black hole's mass precisely and confirm that it's really there, quietly sitting at the heart of our galaxy. Black holes themselves are not the cosmic vacuum cleaners they're often portrayed as in popular media. They don't wander through space, sucking up everything nearby. They simply have strong gravity in their immediate vicinity, just as any massive object would. If the Sun suddenly became a black hole, though it won't happen because the Sun isn't massive enough, the planets would continue orbiting exactly as they do now. Earth wouldn't get pulled in. The Sun's gravitational pull wouldn't change at all. Only the nature of the object at the center would be different. A black hole is simply a region of space where gravity is so strong that not even light can escape from within a boundary called the event horizon. Outside that boundary, gravity falls off with distance, just like anywhere else. Black holes are exotic and extreme, but they follow the same physical laws as everything else in the universe. Supermassive black holes, like the one at the center of the Milky Way, exist at the cores of most large galaxies. They're millions, or even billions of times more massive than the Sun, far larger than black holes formed from collapsing stars. Astronomers aren't entirely sure how they got so big. They may have grown by accreting matter over billions of years, gradually pulling in gas and stars that ventured too close. Or they may have formed early in the universe's history from direct collapse of enormous gas clouds. Either way, they're now permanent fixtures at galactic centers, their immense gravity helping to hold the galaxy together. Stars in the galaxy don't orbit the black hole directly. They orbit the combined gravitational pull of all the stars, gas, and dark matter in the galaxy. The black hole is just one component of that total mass, influential because of its concentrated location at the center, but not dominating the entire galaxy's structure. Dark matter, mentioned briefly just now, is one of the universe's deepest mysteries, and also one of its most calming truths. We know it exists because we can see its gravitational effects, but we can't see the matter itself. Galaxies rotate faster than they should, based on the visible matter alone. Galaxy clusters hold together more strongly than the mass of their stars and gas can account for. Something invisible is providing extra gravity. That something is dark matter, a substance that doesn't emit, absorb, or reflect light, but does interact gravitationally. It makes up about 27% of the universe's total mass and energy, far more than the ordinary matter that forms stars, planets, and people. We don't know what dark matter is made of. It might be an unknown type of particle that only interacts through gravity and possibly through the weak nuclear force. Whatever it is, it's been there since the beginning, shaping the formation of galaxies and large-scale structures, acting as the invisible scaffolding on which the visible universe was built. Despite not knowing what dark matter actually is, astronomers can map where it's located by observing how it bends. Light. Massive objects curve space around them, causing light passing nearby to follow curved paths. An effect called gravitational lensing allows us to detect dark matter by watching how it distorts the appearance of background galaxies. Regions with large amounts of dark matter act like lenses, magnifying and distorting the light from objects behind them. By carefully measuring these distortions, astronomers can create maps showing dark matter's distribution in galaxy clusters and throughout the cosmic web. These maps reveal that dark matter is clumped in certain regions and sparse in others, forming a web-like structure that matches the distribution of visible galaxies. The galaxies sit within the dark matter, like cities along invisible highways, their positions determined by where the dark matter is densest. Understanding dark matter's role in galaxy formation helps explain why galaxies look the way they do. When the universe was young, dark matter clumped together first, forming gravitational wells that attracted ordinary matter. Gas fell into these wells, gathering into dense regions where it could eventually cool and form stars. The first galaxies formed within these dark matter halos, their shapes and structures determined partly by the distribution of dark matter around them. Even today, galaxies are surrounded by extended halos of dark matter that stretch far beyond the visible stars. The Milky Way's dark matter halo likely extends several 100,000 light-years from the galactic center, much farther than the visible disk. The halo contains more mass than all the stars in the galaxy combined. Yet, we can't see it directly. It's there, surrounding us, holding the galaxy together through its gravity, silently and invisibly. An invisible halo reminds us that most of the universe is hidden from direct observation. We can't see dark matter. We can't see dark energy either, a mysterious force causing the universe's expansion to accelerate. Together, dark matter and dark energy make up about 95% of the universe. Only 5% consists of ordinary matter, the stuff that forms stars, planets, and people. At first, the idea that we're made of such a small fraction of the universe's contents might seem disconcerting. But there's something humbling and peaceful about it. The universe doesn't need to be made of the same things we are for us to exist within it. We're a small part of a much larger whole, living in a cosmos dominated by substances we're only beginning to understand. Our existence doesn't require us to be the majority component. We simply need the right conditions, and those conditions exist here, on our planet, in our galaxy, in a tiny visible corner of a mostly invisible universe. The universe's accelerating expansion, driven by dark energy, means that distant galaxies are moving away from us faster and faster as time goes on. Eventually, billions of years from now, galaxies beyond our local group will recede so quickly that their light will no longer reach us. The observable universe will shrink, not because anything is happening to us, but because expansion will carry distant galaxies beyond the horizon of what we can possibly see. In the far future, an observer in the Milky Way might look out and see only the Andromeda galaxy and a few nearby companions. Everything else will have vanished beyond the cosmic horizon, its light stretched to such long wavelengths that it becomes undetectable. It sounds lonely, but it's simply a consequence of expansion. The galaxies are still out there. We just won't be able to see them anymore. And by that time, the Milky Way and Andromeda will have merged into a single, large, elliptical galaxy. Any civilizations present then will have a new home to explore. A merger between the Milky Way and Andromeda, though it won't happen for about 4 billion years, will be a slow and graceful event. The galaxies will approach each other over hundreds of millions of years, their gravity pulling them together. When they first meet, they'll pass through each other, their stars so far apart that none will collide. Gravity will then pull them back for a second pass, and eventually, after several encounters, they'll settle into a single merged galaxy. The process will reshape both galaxies, scattering stars into new orbits, and possibly triggering bursts of star formation, where gas clouds collide and compress. From Earth, if it still exists and still harbours observers, the night sky will change dramatically. Andromeda will grow larger over millions of years, eventually filling much of the sky before the merger completes. Stars from both galaxies will mix, and the Sun, if it hasn't already evolved into a red giant by then, will find itself in a new location within the merged galaxy, following a new orbit around a new centre. Despite all these changes, the fundamental nature of the universe remains constant. Stars will still form from collapsing gas clouds. Planets will still orbit their suns. Gravity will still pull matter together. The laws of physics that govern today's universe will continue operating identically billions of years from now. Galaxies may merge, stars may die, the universe may expand, but the underlying order persists. Constancy provides a deep sense of stability. No matter what happens to individual objects, the rules governing their behavior never change. The cosmos is not chaotic or random. It follows patterns, obeys laws, and unfolds in ways we can predict and understand. And within an orderly universe, structures like stars, planets, and perhaps life continue to arise, generation after generation, as they have for billions of years, and will for billions more to come. Gravity's patience in shaping the universe extends to even the smallest scales. Individual atoms don't feel gravitational attraction to each other in any meaningful way. The force is far too weak at such tiny distances. But gather enough atoms together, and their combined gravitational pull becomes significant. A few thousand atoms can hold together as a dust grain. Trillions of dust grains can clump into asteroids. Asteroids can merge into planets. Planets can form around stars. Stars can gather into galaxies. Each step builds on the previous one, gravity working consistently across all scales, from the microscopic to the cosmic. It never stops, never weakens, never changes its fundamental nature. Whether pulling together dust grains in a nebula or holding galaxy clusters together across millions of light years, gravity follows the same simple rule. Every bit of mass attracts every other bit of mass. The universe is held together by the weakest of the fundamental forces, acting patiently over vast stretches of time and space. Weak though it may be compared to other forces, gravity shaped not just where matter ended up, but when events occurred in the universe's history. Shortly after the beginning, when the universe was less than a second old, it was far too hot and dense for atoms to exist. Matter existed only as a soup of fundamental particles, bouncing off each other at incredible speeds. As space expanded and cooled, particles could finally stick together to form the first atomic nuclei, mostly hydrogen and helium. But even then, the universe was too hot for electrons to settle into stable orbits around those nuclei. Photons, particles of light, scattered constantly off the free electrons, making the universe opaque like a thick fog. Only after about 380,000 years, when the temperature finally dropped enough, could electrons bind to nuclei and form complete atoms. At that moment, photons could travel freely through space for the first time. The universe became transparent, and the light from that moment has been traveling through space ever since, cooling and stretching as the universe expanded. We can still see that ancient light today. It comes from all directions in the sky as a faint microwave glow called the cosmic microwave background. Detecting it required sensitive instruments because it's been stretched by expansion from visible light to microwave wavelengths, corresponding to a temperature of only about -454 degrees Fahrenheit, just a few degrees above absolute zero. Yet it's there, filling all of space, a perfect relic from when the universe first became transparent. Maps of the cosmic microwave background show tiny temperature variations, regions that were slightly warmer or cooler than average. Those variations, only about 1 part in 100,000, were the seeds from which all structure in the universe grew. Slightly denser regions had slightly stronger gravity, which pulled in more matter, which increased the gravity further, which pulled in even more matter. Over hundreds of millions of years, those tiny initial differences amplified into the galaxies, galaxy clusters, and cosmic web we see today. Everything started from almost nothing, from fluctuations so small they were nearly undetectable, grown through the patient action of gravity into the rich structure of the modern universe. Patience like that characterizes so many cosmic processes. Stars don't form instantly when gas clouds collapse. The process takes millions of years as material slowly falls inward, heats up from compression, and eventually reaches temperatures high enough to ignite fusion. Even then, fusion itself is remarkably slow. In the Sun's core, where temperatures reach about 27 million degrees Fahrenheit, any given proton waits on average about 10 billion years before successfully fusing with another proton. Individual fusion reactions happen constantly because there are so many protons, but each one is a rare event. The Sun doesn't burn like fire. It glows because countless rare events add up. Nuclear fusion releases energy gradually, steadily, providing a stable output that has remained nearly constant for billions of years. If fusion happened faster, stars would burn out quickly and could never provide the stable environments that planets need to develop and maintain life. The slowness isn't a limitation. It's what makes stellar lifetimes so long and planetary systems so stable. Stability extends beyond individual stars to the patterns we see when we look at the night sky. Constellations, those familiar patterns formed by bright stars, have appeared roughly the same for all of recorded human history. The stars that make up Orion or the Big Dipper have been in essentially the same positions relative to each other for thousands of years. Ancient astronomers saw the same patterns we see today, yet the stars are moving. They orbit the galaxy just like the Sun does, each following its own path. Over tens of thousands of years, the constellations will gradually shift and distort as stars move at different speeds in different directions. Eventually, the familiar patterns will dissolve completely, replaced by new arrangements. But the timescale is so long that from a human perspective, the sky appears fixed and unchanging. The same stars that guided ancient sailors still mark the same positions for us today. The universe's motion happens on scales far longer than human civilizations, providing a sense of permanence, even though nothing is truly static. Among the stars visible in our night sky, many are not single suns like ours, but binary or multiple star systems, where two or more stars orbit each other. In fact, binary systems are more common than single stars. About half of all sun-like stars have at least one companion. Some pairs orbit so close together that they nearly touch, completing their mutual orbit in just hours or days. Others are separated by thousands of astronomical units, taking millions of years to complete a single orbit. The stars in a binary system formed together from the same collapsing gas cloud, and they've remained gravitationally bound ever since. From a planet orbiting one star in such a system, the sky would offer a spectacular view. There might be 2 sunrises and 2 sunsets each day, or, depending on the configuration, the companion star might appear as an extremely bright point in the night sky, far brighter than any planet or even the full moon. Life on such a planet would experience very different day-night cycles than we do on Earth, but the system could still be stable, the orbits predictable, the environment potentially suitable for life. Predictability in orbital dynamics allows some binary star systems to create beautiful cosmic phenomena. When 2 stars orbit each other, they occasionally align so that one passes in front of the other from our perspective. The nearer star blocks light from the farther one, causing the system's total brightness to dip temporarily. These eclipsing binary systems provided some of the earliest accurate measurements of stellar masses and sizes. By watching how long the eclipse lasts and how much the brightness decreases, astronomers can calculate the star's diameters and orbital speeds. The math is straightforward, relying only on geometry and Kepler's laws of motion. It's remarkable that we can measure the size of a star that's hundreds or thousands of light years away, simply by watching how its light changes over time. The universe reveals its secrets through patterns, through predictable cycles that repeat endlessly. Even distant objects follow rules we can understand and use to learn about them. Learning about distant objects through their light extends to understanding their composition. Every element produces a unique pattern of spectral lines, specific wavelengths of light that it absorbs or emits. Hydrogen produces one set of lines, helium another, iron yet another. By splitting starlight into a spectrum and examining which lines appear, astronomers can determine what elements exist in the star's atmosphere. The same technique works for galaxies, nebulae, and even planets. We've used it to discover that the universe is made primarily of hydrogen and helium, with heavier elements making up only a small fraction of the total. We've used it to measure temperatures, densities, and motions of distant objects. We've even used it to detect planets around other stars by watching for tiny shifts in their parent star's spectral lines caused by the planet's gravitational tug. Light carries information, and we've learned to read it like a book, extracting details about objects we'll never visit and could never touch. Reading light from distant galaxies reveals another fascinating aspect of cosmic history. The farther away a galaxy is, the faster it appears to be moving away from us, a relationship discovered by astronomer Edwin Hubble in the 1920s. But the galaxies aren't actually moving through space in the normal sense. Space itself is expanding between us and them. We can tell this Because the light from distant galaxies is redshifted, stretched to longer wavelengths by the expansion. The amount of redshift tells us how much the universe has expanded since the light was emitted. A galaxy with a redshift of 1 has light that's been stretched by a factor of 2, meaning the universe has doubled in size since that light left the galaxy. A galaxy with a redshift of 2 has light stretched by a factor of 3. By measuring redshifts of many galaxies at different distances, astronomers have mapped out how the universe's expansion rate has changed over time. It was faster in the past, slowed down for several billion years, and then, recently, in cosmic terms, began accelerating again. The expansion history is written in the light from distant galaxies, waiting to be decoded. Acceleration of cosmic expansion surprised astronomers when it was discovered in the late 1990s. Before then, most scientists assumed expansion was gradually slowing down due to the mutual gravitational attraction of all matter in the universe. Measurements of distant supernovae, explosions that can be used as standard candles to measure cosmic distances, revealed instead that expansion is speeding up. Something is pushing the universe to expand faster over time, and that something has been named dark energy. We don't know what it is. It might be a property of space itself, a kind of energy inherent in empty space that increases as space expands. Or it might be a new field pervading the universe, something we haven't discovered yet. Whatever its nature, dark energy makes up about 68% of the universe's total energy content. It's the dominant component, more abundant than both ordinary matter and dark matter combined. Yet, its effects are only noticeable on the largest scales, causing the acceleration of cosmic expansion. On smaller scales, like within galaxies or even galaxy clusters, gravity remains dominant, and dark energy's influence is negligible. Negligible though its local effects may be, dark energy will eventually shape the ultimate fate of the universe. If it continues driving accelerated expansion, galaxies beyond our local group will gradually disappear from view, receding faster than light can catch up to us. Eventually, only the merged Milky Way Andromeda galaxy will remain visible. Star formation will continue for a while, as remaining gas collapses into new stars. But eventually, the gas supply will run out. No new stars will form. Existing stars will age and die. The massive ones exploding as supernovae. The smaller ones slowly cooling into white dwarfs. Over trillions of years, the universe will grow darker and colder. Galaxies will become graveyards of stellar remnants. Dead worlds orbiting dead stars. Even black holes won't last forever. Through a quantum process called Hawking radiation, they'll gradually evaporate, taking unimaginably long times to do so, but eventually vanishing. The universe will end not with a bang, but with a whisper, fading into a cold, dark, nearly empty expanse. But that's so far in the future, trillions upon trillions of years from now, that it bears no relevance to anything happening today. For now, the universe is young, vibrant, filled with stars and galaxies, and will remain so for billions of years to come. Billions of years from now, long before the universe grows cold and dark, our own sun will undergo its transformation into a red giant. The change will be gradual but profound. As hydrogen in the core runs out, fusion will slow down, causing the core to contract under its own weight. Contraction will heat the core, which will ignite a shell of hydrogen surrounding it. The energy from this shell burning will push the sun's outer layers outward, swelling the star to enormous size. At its largest, the Sun might extend to Earth's current orbit or even beyond. The outer layers will be cool compared to the core, giving the star a reddish appearance, hence the name red giant. From Earth, if the planet survives, the sky would be dominated by a vast, dim red sun, filling a huge portion of the heavens. Temperatures on the surface would be far too hot for liquid water, and Earth's atmosphere would likely boil away into space. But the process takes hundreds of millions of years, plenty of time for life, if it still exists, to adapt or move elsewhere. Moving elsewhere might not be as impossible as it sounds. While interstellar travel remains firmly in the realm of science fiction for now, the basic physics doesn't forbid it. Nothing in the laws of nature prevents a spacecraft from traveling to another star, given enough time and energy. The distances are vast. The nearest star, Proxima Centauri, is about 4 light-years away, meaning light takes 4 years to cover that distance. With current technology, a spacecraft would take tens of thousands of years to reach even the nearest stars. But future technologies might reduce that time dramatically. Proposals for laser-driven light sails or fusion-powered rockets could potentially reach a few % of the speed of light, reducing travel time to nearby stars to decades or centuries. Even generation ships, enormous vessels where people live out their entire lives while traveling between stars, are theoretically possible. The universe doesn't forbid interstellar travel. It just requires patience, resources, and technological advances we haven't yet achieved. The cosmos is accessible in principle, even if not in practice, at least not yet. Accessibility in principle extends to understanding cosmic phenomena through physics and mathematics. The equations governing the universe aren't mysterious or unknowable. They're often elegant and surprisingly simple. Einstein's famous equation, E=mc², relates energy and mass with just 3 symbols. Newton's law of gravitation describes how objects attract each other with a single equation. Maxwell's equations, which describe all of electromagnetism, fit on a single page. Schrödinger's equation, fundamental to quantum mechanics, is compact and precise. These aren't approximations or guesses. They're exact descriptions of how nature works, tested countless times, and never found wanting within their domains of applicability. The universe operates on mathematical principles, and those principles are comprehensible to human minds. We're capable of understanding the cosmos, not just through observation, but through deep theoretical insight. The fact that the universe is comprehensible, that it follows rules we can discover and express in mathematics, is perhaps one of its most beautiful properties. Beauty in physics equations often reflects deeper truths about symmetry and conservation. Many fundamental laws arise from symmetries in nature. For instance, the fact that physics works the same way everywhere in space leads directly to conservation of momentum. The fact that physics works the same way at all times leads to conservation of energy. The fact that physics doesn't depend on which direction you're facing leads to conservation of angular momentum. These aren't coincidences. They're deep connections between the structure of space and time and the laws governing motion and energy. Emmy Noether, a mathematician working in the early 20th century, proved these connections mathematically, showing that every symmetry corresponds to a conserved quantity. Her theorem is considered one of the most important results in theoretical physics. It reveals that the universe's laws aren't arbitrary. They emerge from the fundamental properties of space and time itself. The cosmos is not just orderly, but elegantly designed, in the sense that its structure naturally gives rise to the conservation laws that make complex, stable systems possible. Stability arising from conservation laws allows complex structures like galaxies to persist for billions of years. A galaxy contains hundreds of billions of stars, each orbiting the galactic center, each following its own path. Yet, the galaxy maintains its overall structure despite this complexity. Stars pass through the spiral arms, which are actually density waves rather than fixed structures, like cars slowing down in traffic. The arms appear bright because stars spend more time there, crowded together temporarily before moving on. Individual stars orbit the galaxy at different speeds, depending on their distance from the center. But the overall pattern persists. Angular momentum is conserved. Energy is conserved. These conservation laws ensure that the galaxy doesn't fly apart or collapse, but maintains a stable, though gradually evolving, configuration over cosmic time. We can observe galaxies billions of light years away, meaning we're seeing them as they were billions of years ago, and they look similar to nearby galaxies we see in the present. Galaxies are long-lived, stable structures, and that stability comes from fundamental physical laws that have operated unchanged since the universe began. Fundamental laws operating unchanged across cosmic history means that the universe has always been comprehensible in principle, even though we've only recently developed the tools to understand it. Early in the universe's history, when the first stars were forming, the same laws of physics that govern today's stars were already in effect. Gravity pulled gas clouds together. Compression heated the gas. Fusion ignited when temperatures reached critical thresholds. The first stars, made purely of hydrogen and helium without heavier elements, probably looked different from modern stars. They might have been more massive, burning hotter and brighter, living shorter lives. But they followed the same rules. They formed, shone, evolved, and died according to principles we can understand today. The universe's comprehensibility is timeless. What was true about physics billions of years ago remains true today and will remain true billions of years hence. Timelessness of physical laws provides a profound sense of cosmic stability. Gravity won't suddenly stop working. Light won't change its speed. Atoms won't begin behaving differently. The constants of nature, those fundamental numbers that appear in physics equations, like the speed of light, the gravitational constant, and the charge of an electron, appear to be truly constant. Measurements of distant galaxies show that these constants had the same values billions of years ago as they do today. Theoretical physicists have searched for evidence that constants might vary with time or location, and so far they've found none. The universe plays by the same rules everywhere and always. Changes occur, certainly. Stars are born and die. Galaxies evolve. The universe expands. But the underlying laws governing these changes remain fixed. It's like a game where the pieces move and the board changes, but the rules stay the same. Knowing this brings a kind of comfort. The cosmos is vast and ancient and will exist long after we're gone. But it's not arbitrary or capricious. It follows rules, and those rules don't change. Rules governing the cosmos include not just the grand laws of physics, but also the detailed chemistry that makes life possible. Carbon, the basis of all known life, has a special property. it can form 4 bonds with other atoms, allowing it to create complex molecules with intricate structures. Chains, rings, branches, 3-dimensional frameworks, all are possible with carbon chemistry. No other element offers the same versatility. Silicon comes close, also forming 4 bonds, but silicon compounds are generally less stable and less diverse than carbon compounds. The chemistry of life as we know it depends critically on carbon's properties, and those properties are determined by the structure of the carbon atom, specifically how its electrons arrange themselves around the nucleus. That structure, in turn, comes from quantum mechanics, the physics governing matter at atomic scales. In a sense, life is a consequence of quantum mechanics operating through chemistry. The deepest laws of physics enable the chemistry that enables biology. Everything connects. Connections between different scales and different phenomena characterize much of our understanding of the universe. The formation of planets connects to stellar nucleosynthesis, which connects to galaxy evolution, which connects to cosmic expansion. Water on Earth arrived partly from comets, which formed in the outer solar system, which condensed from the disk of material surrounding the young sun, which collapsed from a molecular cloud enriched by previous generations of stars. Every part of the story links to others. Nothing exists in isolation. Even seemingly simple questions, like why the sky is blue, have answers that touch on multiple areas of physics. Sunlight interacts with air molecules through electromagnetic forces. Shorter wavelengths scatter more than longer wavelengths, a consequence of how light waves interact with particles much smaller than the wavelength. Blue light scatters throughout the atmosphere, making the sky appear blue from any direction, while direct sunlight, with its blue component removed by scattering, appears more yellow. The redness of sunsets comes from the same effect amplified by the greater thickness of atmosphere. Sunlight passes through near the horizon. Simple observations connect to deep physics. Deep physics often reveals surprising facts that contradict our intuitions. For instance, orbiting spacecraft don't float in zero gravity because there's no gravity at their altitude. They float because they're continuously falling toward Earth, but moving forward fast enough that they keep missing it. Orbit is simply a state of perpetual free fall. Gravity at the altitude of the International Space Station is only about 10% weaker than at Earth's surface, certainly strong enough to pull objects down. But because the station and everything in it are falling together at the same rate, objects inside appear weightless relative to their surroundings. Astronauts experience the same sensation you'd feel in an elevator, whose cables snapped, except the sensation continues indefinitely, because the spacecraft's forward motion prevents it from hitting the ground. It's a somewhat unnerving thought at first, but also oddly peaceful. Orbit is just falling endlessly, the spacecraft and its occupants following the natural curved path through spacetime created by Earth's mass. Spacetime itself is a concept that took centuries to fully understand. For most of history, people thought of space and time as separate, independent entities. Space was the 3-dimensional arena in which things happened. Time was the universal clock ticking away in the background. Einstein's theory of relativity united them into a single 4-dimensional continuum called space-time. Objects don't move through space as time passes. They move through space-time, following paths called world lines. What we perceive as gravity, the force pulling objects together, is actually the curvature of space-time caused by mass and energy. Massive objects like stars and planets curve space-time around them, and other objects simply follow the straightest possible paths through that curved geometry. Those paths appear curved in three-dimensional space, which we interpret as gravitational attraction. But in four-dimensional space-time, the paths are as straight as possible given the curvature. There's no force pulling objects together, just objects following the natural geometry of space-time. It's a beautiful reframing of gravity from a force to a consequence of geometry. Geometry of space-time becomes especially interesting near very massive objects. Near a black hole, space-time curves so extremely that not even light can escape from within the event horizon. But outside the event horizon, space-time is merely strongly curved, not infinitely so. A spacecraft could orbit a black hole just as it orbits a star, though it would need to be careful not to get too close. The region just outside the event horizon is called the ergosphere in rotating black holes. Space-time there is dragged around by the black hole's rotation, forcing everything to move in the direction of rotation, whether it wants to or not. Yet, even in this extreme environment, objects still follow predictable paths determined by the geometry of space-time. Mathematicians and physicists have calculated precisely what those paths look like. They've made visualizations showing how a black hole would appear, with the distorted images of background stars creating rings of light. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, the image matched theoretical predictions almost perfectly. Even the most extreme objects in the universe behave according to understood laws. Understood laws allow us to predict not just what we can see, but also what we can't. Gravitational waves, ripples in space-time itself, were predicted by Einstein's equations in 1916, but they weren't detected until 2015, nearly a century later. The detection required incredibly sensitive instruments, capable of measuring changes in distance smaller than a proton's diameter. When two black holes, or neutron stars, spiral together and merge, they release enormous amounts of energy as gravitational waves, causing space itself to oscillate. These waves spread outward at the speed of light, passing through everything in their path. When they reach Earth, they stretch and compress space by tiny amounts, which specialized detectors called interferometers can measure. The first detection came from two black holes merging over 1 billion light-years away, an event that happened more than 1 billion years ago. The waves traveled through space all that time, carrying information about the merger. When they finally reached Earth, they caused mirrors in a kilometers-long detector to shift by less than 1,000th the diameter of a proton. Yet, we measured it, confirmed the detection, and extracted details about the black holes that merged. The universe reveals itself through subtle whispers, as well as through bright light. Subtle whispers from the cosmos remind us how quiet space actually is. Sound requires a medium, molecules of air or water or some other material, to vibrate and carry the wave. In the vacuum of space, there's no medium, so sound can't propagate. Explosions in space would be silent. Colliding asteroids wouldn't make noise. Even the powerful jets of material blasting from black holes and the shock waves from supernovae, though they carry enormous energy, don't produce sound waves we could hear. They might create vibrations in gas clouds that could theoretically be translated into sound if we could somehow listen to them. but the frequencies would be far too low for human hearing. The universe is mostly silent, filled with electromagnetic radiation we can detect with telescopes, but lacking the acoustic cacophony we might imagine. There's something peaceful about that. The cosmos goes about its business quietly, light traveling silently through the void, galaxies rotating without a whisper, the only sounds being those we create ourselves as we explore and observe from our small world. Our small world provides a unique vantage point for observing the universe. Earth's atmosphere, while it blocks some wavelengths of light and distorts observations by causing stars to twinkle, also protects us from harmful radiation and creates the blue sky we see during the day. Without an atmosphere, the sky would be black even at noon, with the sun appearing as an extremely bright point against darkness. Stars would be visible during the day. The moon would look the same, whether it's daytime or nighttime. It's hard to appreciate how much atmosphere affects what we see until we imagine what the view would be like without it. Astronauts in space see the sun and stars simultaneously against blackness, an alien vista that's nonetheless completely natural, simply what the universe looks like without atmospheric filtering. Observations from space-based telescopes like Hubble and James Webb avoid atmospheric distortion, capturing sharper images and detecting wavelengths that Earth's atmosphere blocks. But ground-based observatories have their own advantages, including larger sizes and easier maintenance. We use both approaches, combining space-based and ground-based observations to build the most complete picture possible of the cosmos. Building complete pictures requires not just optical telescopes, but instruments that detect other wavelengths. Radio telescopes listen to radio waves from space, revealing phenomena invisible to optical telescopes. Pulsars, rapidly rotating neutron stars that emit beams of radio waves, were discovered through radio observations. The cosmic microwave background was first detected by radio astronomers. X-ray telescopes, which must operate in space because Earth's atmosphere blocks X-rays, reveal the universe's high-energy phenomena, like black holes actively feeding on material, and the hot gas in galaxy clusters. Infrared telescopes see through dust clouds that block visible light, allowing us to peer into star-forming regions and see through the galactic center to observe stars orbiting the central black hole. Gamma-ray telescopes detect the most energetic photons in the universe, produced by supernova, gamma-ray bursts, and matter falling into black holes. Each wavelength reveals different aspects of cosmic phenomena. Together, they provide a comprehensive view that wouldn't be possible using visible light alone. The universe speaks in many languages, and we've learned to listen to all of them. Listening to the universe in multiple wavelengths reveals that some of the most violent events can have peaceful outcomes. Supernovae, despite their tremendous power, ultimately enrich the interstellar medium with heavy elements and trigger new star formation by compressing nearby gas clouds. The violence serves a purpose in the cosmic cycle. Galaxies sometimes collide, a process that sounds catastrophic, but actually unfolds over hundreds of millions of years. Stars pass through each other without colliding because they're so far apart. Gas clouds do collide, compressing and triggering bursts of new star formation. Eventually, the galaxies merge, their stars settling into new orbits around a common center. The result is often a large elliptical galaxy, its stars moving in random orbits rather than the organized disk of a spiral galaxy Even black holes, which we tend to think of as destructive, play constructive roles. Material falling toward a black hole heats up and radiates energy, sometimes producing jets that inject energy into surrounding gas, regulating star formation and influencing the evolution of entire galaxies. Violence and creation are intertwined in the cosmos, each enabling the other. Intertwined processes characterize galaxy evolution over cosmic time. Galaxies don't form in isolation and then remain unchanged. They grow by accreting gas from their surroundings and by merging with other galaxies. Star formation rises and falls depending on gas availability. Black holes at galactic centers grow as they consume material, and their activity can heat surrounding gas enough to suppress star formation temporarily. Some galaxies have vigorous star formation, producing new stars at rates of hundreds or thousands of solar masses per year. Others, called quiescent or dead galaxies, have little or no ongoing star formation. They've either consumed all their available gas or had it stripped away by interactions with other galaxies or blown away by energetic processes. Yet, even quiescent galaxies can be reawakened if they encounter fresh supplies of gas, perhaps from a merger with a gas-rich companion. Galaxies cycle through different states, their evolution shaped by internal processes and external interactions. They're dynamic systems, constantly changing, even if individual changes happen too slowly for us to see in a human lifetime. Change happens slowly on cosmic scales, but inexorably. Mountains rise and erode over millions of years. Continents drift across Earth's surface, their positions changing measurably over human lifetimes, but dramatically over geological epochs. Stars exhaust their fuel and die. New ones form, the galactic population slowly turning over. Even space itself expands, carrying distant galaxies away from us, the universe growing larger with each passing moment. Yet, within this context of slow change, some things remain remarkably stable. The laws of physics don't change. The constants of nature stay constant. Atoms have the same properties today as they did billions of years ago. The speed of light remains fixed. In a changing universe, these immutable aspects provide anchors, reliable foundations on which everything else is built. We can count on certain things remaining true, even as others evolve and transform. Change and stability coexist, neither one dominating completely, creating a universe that's both dynamic and reliable. Reliability in natural laws allows us to reconstruct the universe's history with confidence. By working backward from current observations, astronomers have traced cosmic evolution from the present day back to the earliest moments after the beginning. The universe started hot and dense, expanded rapidly, cooled as it expanded, allowing particles to form, then atoms, then the first structures. Tiny density fluctuations grew under gravity into stars and galaxies. The first stars formed a few 100 million years after the beginning, igniting fusion and lighting up the previously dark universe in what's called the cosmic dawn. These earliest stars were massive and short-lived, exploding quickly and seeding space with heavier elements. Successive generations of stars formed from increasingly enriched material. Galaxies grew through mergers and accretion. The universe evolved from simple to complex, from uniform to structured, from darkness to light. We can trace this evolution because the laws that governed it are knowable, and because light from different distances shows us the universe at different ages. The cosmic past is written in the light, reaching us from distant objects. Written in light, the cosmic past becomes accessible, even though we can't travel backward in time to witness events directly. When we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. The light has been traveling toward us all that time, carrying information about what the galaxy looked like when the light left. By observing many galaxies at different distances, we see snapshots of cosmic history at different times. Nearby galaxies show us what the universe looks like now. Distant galaxies show us what it looked like in the past. By comparing these populations, we can see how galaxies have evolved. Early galaxies tend to be smaller, more irregular and bluer, indicating active star formation. Nearby galaxies are more diverse, including large ellipticals that have stopped forming stars and massive spirals with organized structures. The transition from early to late types involves mergers, star formation driven by gas accretion, and feedback from supernova and black holes. Each galaxy we observe is a piece of the puzzle, and together they tell the story of cosmic evolution. Cosmic evolution includes not just galaxies, but also the structure of space itself. The universe started with a period of extremely rapid expansion called inflation, which occurred in the first tiny fraction of a second after the beginning. During inflation, space expanded faster than the speed of light, not through anything moving through space faster than light, which is impossible, but through space itself expanding. The expansion stretched the universe from sub-microscopic scales to cosmic scales in an instant. It solved several puzzles about why the universe appears so uniform in different directions, and why it's geometrically flat rather than curved. After inflation ended, expansion continued at a much slower rate, driven by the matter and energy present in the universe. For billions of years, gravity gradually slowed the expansion rate. Then, as matter density decreased due to ongoing expansion, dark energy's influence became dominant, causing expansion to accelerate. The universe's expansion history is complex, with different eras dominated by different components. But each era follows naturally from the laws of physics and the contents of the universe at that time. Contents of the universe have changed over time in their relative importance. In the earliest moments, radiation dominated, meaning most of the universe's energy was in the form of photons and other massless or nearly massless particles. As the universe expanded, radiation cooled and its energy density decreased faster than that of matter. Eventually, matter became the dominant component, and the universe entered the matter-dominated era. Galaxies formed during this era, gravity pulling matter together into structures. More recently, as matter continued to thin out due to expansion, dark energy became dominant. Now we live in a dark, energy-dominated era, where accelerated expansion is the main driver of cosmic evolution. Looking ahead, billions of years, dark energy will continue to dominate, driving galaxies apart, reducing the observable universe, and eventually leaving isolated island universes separated by voids they can never cross. But that's so far in the future that it remains firmly theoretical. For now, and for billions of years to come, the universe remains in a state where structure persists, stars shine, and complex phenomena continue to unfold. Complex phenomena include the possibility of life arising not just on Earth, but elsewhere in the universe. While we haven't yet detected definitive signs of extraterrestrial life, the sheer number of potentially habitable worlds suggests it's possible, perhaps likely. The discovery of thousands of exoplanets, many in their stars' habitable zones, has transformed the question from whether Earth-like planets exist to how common they are, and whether they typically harbour life. We're developing techniques to detect biosignatures, signs of life in exoplanet atmospheres. Certain combinations of gases, like oxygen and methane together, might indicate biological activity, because these gases react with each other and wouldn't persist together without continuous replenishment. Detecting such signatures would require extremely sensitive observations, probably from next-generation space telescopes. Even then, interpretation would be challenging. We have to be careful not to assume that alien life would produce the same chemical signatures as Earth life. But the search continues, driven by the profound implications of the question: are we alone? The universe is vast enough that either answer feels incredible. If we're alone, life is extraordinarily rare and precious. If we're not, we're part of a cosmic community, connected to other beings through the shared chemistry of life. Shared chemistry connects all life on Earth through common ancestry, and it might connect us to alien life if it exists. The elements necessary for life, particularly carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are common throughout the universe. They're produced in stars and scattered by supernovae. They exist in interstellar space, in comets, in meteorites, and presumably on countless planets. The chemistry of life is the chemistry of the universe. While we can't be certain that alien life would use the same biochemistry as Earth life, it's likely that any life using liquid water as a solvent would rely on similar elements, and perhaps similar molecular structures. Carbon's ability to form complex molecules makes it an excellent basis for life, though some scientists have speculated about silicon-based life, or life using other solvents besides water. Regardless of the details, life anywhere would need to gather energy, maintain organization against entropy, reproduce, and evolve. These fundamental requirements would shape alien biology, even if the specific implementations differ from Earth's. We might find that life, wherever it arises, follows similar principles, even if it looks very different from what we're familiar with. Familiarity with Earth's life often colors our expectations about alien life, but the universe might surprise us with its creativity. Life on Earth is incredibly diverse, occupying nearly every environment, from deep ocean vents to high-altitude clouds, from frozen Antarctic rocks to boiling hot springs. Some organisms thrive in conditions we'd consider extreme, tolerating pressures, temperatures, acidities, or radiation levels that would destroy most life. These extremophiles demonstrate that life's boundaries are broader than we once thought. If Earth life can adapt to such varied conditions, perhaps alien life has adapted to environments we'd never consider habitable. There might be life in the subsurface oceans of icy moons, like Europa or Enceladus, surviving on chemical energy rather than sunlight. There might be life on planets with atmospheres nothing like Earth's, breathing gases we'd find toxic. There might be life forms that exist at very different scales, microscopic, or perhaps even larger than anything on Earth. The universe has had billions of years to experiment with different approaches to life, and we've only just begun searching for the results of those experiments, searching for signs of life. Beyond Earth includes looking for technological signatures as well as biological ones. The search for extraterrestrial intelligence, or SETI, listens for radio signals or other signs of advanced civilizations. If intelligent life exists elsewhere and has developed technology, it might intentionally or unintentionally broadcast signals into space. Radio telescopes scan the sky looking for patterns that couldn't be produced by natural processes, signals that would indicate an artificial origin. So far, no confirmed detections have been made, though there have been intriguing candidates that turned out to have mundane explanations. The lack of detection doesn't mean intelligence is rare. Space is vast, and signals weaken rapidly with distance. We've only searched a tiny fraction of possible stars at a limited range of frequencies. A civilization would need to be broadcasting powerfully enough, and at frequencies we're monitoring, for us to detect them. Even then, the signal would take years or centuries to reach us depending on distance. SETI is a patient search, one that may take decades or centuries to succeed, if it succeeds at all. But the potential reward, confirming we're not alone, makes the search worthwhile. Worthwhile searches often require sustained effort over long periods, and astronomy is full of examples where patience paid off. Discovering exoplanets required decades of instrument development before telescopes became sensitive enough to detect them. Understanding the universe's expansion history required observations of distant supernovae from multiple telescopes over many years. Mapping the cosmic microwave background required satellite missions that spent years collecting data from every direction in the sky. Science progresses incrementally, each discovery building on previous work, each generation of scientists extending the knowledge accumulated by earlier generations. We understand the universe better now than we did a century ago, and scientists a century from now will understand it better still. There's no final endpoint where all questions are answered. Each answer opens new questions. Each discovery reveals new mysteries. The process continues, driven by curiosity and the satisfaction of understanding even small pieces of the cosmic puzzle. Puzzles in cosmology remain despite our progress. We don't know what dark matter is, though we can measure its effects. We don't know what dark energy is, though we can see its influence on cosmic expansion. We don't know if our universe is the only one, or if it's part of a larger multiverse. We don't know what happened at the very moment of the beginning, or even if beginning is the right word for it. We don't know how common life is, or whether intelligence inevitably develops given enough time. These unknowns don't diminish our achievements. They motivate further exploration. Science thrives on questions. The fact that mysteries remain means there's still work to do, still discoveries waiting to be made. And even if we someday answer today's questions, new ones will surely emerge. The universe is deep and complex, layered with phenomena operating at different scales and energies. We'll never run out of things to investigate, never reach a point where everything is known. There will always be a frontier, always something new to explore, always another layer of understanding waiting to be uncovered. Uncovered layers of understanding often reveal that the universe is stranger and more wonderful than we imagined. Quantum mechanics, the physics of the very small, describes a world where particles can exist in multiple states simultaneously until observed, where entanglement connects particles across arbitrary distances, where uncertainty is fundamental rather than just a consequence of imperfect measurements. These phenomena seem bizarre because they're far removed from everyday experience. we don't see quantum effects in daily life because they're washed out by interactions with the environment at larger scales. But they're real, and they've been confirmed by countless experiments. Technologies like transistors, lasers, and MRI machines rely on quantum mechanics. The universe, at its smallest scales, operates according to rules very different from the classical physics that governs large objects. Yet, quantum mechanics and classical physics connect smoothly. The quantum world gives rise to the classical world when enough particles interact. There's no contradiction, just different descriptions appropriate for different scales. The universe is self-consistent, its various layers fitting together even when they seem individually strange. Strangeness at quantum scales contrasts with the orderliness of larger systems, but both reflect the same underlying laws. A planet orbiting a star is a classical system, its motion described by Newton's laws or Einstein's relativity, depending on the required precision. The atoms in the planet and star are quantum systems, their behavior described by quantum mechanics. Yet, the quantum particles collectively produce the classical motion. Wave functions, the quantum description of particle states, average out over trillions upon trillions of atoms to produce definite positions and velocities. The uncertainty inherent in individual particle properties becomes negligible when dealing with macroscopic objects. A planet doesn't exist in a superposition of multiple orbits. Its orbit is well defined because quantum uncertainties are too small to matter at that scale. The transition from quantum to classical is smooth and understood. Different descriptions apply at different scales, but they're all part of a unified framework describing nature at every level. Unified frameworks that connect different phenomena have been a goal of physics for centuries. Electricity and magnetism, once thought to be separate forces, were unified by Maxwell's equations into electromagnetism. Electromagnetism and the weak nuclear force were later unified into the electroweak force. Physicists hope to eventually unify all fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single theoretical framework, often called a theory of everything. Such a theory would describe all physical phenomena using a single set of principles, explaining how the different forces arise from more fundamental symmetries. Progress has been made. The standard model of particle physics successfully describes 3 of the 4 forces, all except gravity. Incorporating gravity remains challenging because it behaves differently from the other forces, requiring a quantum theory of gravity that we haven't yet fully developed. But the goal remains, and progress continues. Even if a complete theory of everything proves elusive, the search itself advances our understanding and reveals new connections between phenomena we once thought were unrelated. Related phenomena often turn out to share deeper connections than initially apparent. The curvature of space-time that causes gravity is related to the quantum fields that describe particles. Black holes, purely gravitational objects, according to classical general relativity, emit thermal radiation according to quantum mechanics, suggesting deep connections between gravity, thermodynamics, and quantum physics. Some physicists believe space-time itself might emerge from more fundamental quantum entities, that what we perceive as smooth, continuous space is actually a large-scale approximation of something discrete and quantum at the smallest scales. These ideas remain speculative and not fully developed, but they hint at how different areas of physics might ultimately unify into a coherent whole. The universe presents itself to us in apparently different guises, particles and waves, matter and energy, space and time. But underlying these distinctions might be a simpler, more unified description. We're still searching for that description, still working to see how the pieces fit together, still discovering connections that weren't obvious before. Obvious connections are sometimes the most profound. Earth orbits the Sun orbits the galaxy is part of a cluster moving through space, and all of it exists within an expanding universe. Each level of structure nests within larger ones, from atoms to molecules, to cells, to organisms, to planets, to solar systems, to galaxies, to galaxy clusters, to superclusters. The scales span roughly 60 orders of magnitude, from the smallest subatomic particles to the observable universe. At each scale, different forces dominate, and different phenomena become important. Quantum mechanics governs atomic scales. Chemistry governs molecular scales. Biology governs cellular and organismal scales. Gravity governs astronomical scales. Yet, it's all connected. The same particles that form atoms also form stars. The same forces that hold molecules together also hold planets in their orbits when you trace through the causal chains. The universe is a hierarchy of structures, each level built on the previous one, each operating according to natural laws that follow consistently from the fundamental principles of physics. Principles of physics apply with equal validity everywhere we can observe. Stars in distant galaxies follow the same nuclear physics as our Sun. Planets orbiting other stars follow the same gravitational laws as planets in our solar system. Light from the early universe obeys the same electromagnetic theory as light emitted by a lamp. This universality is remarkable and not logically necessary. We could imagine a universe where the laws of physics varied from place to place or changed with time. But that's not the universe we inhabit. Our cosmos is governed by consistent, universal principles that hold everywhere and always. This universality is what makes cosmology possible as a science. We can study the entire universe, even regions we'll never visit, because we trust that the same laws operate there as here. Observations of distant objects can be interpreted using physics tested in laboratories on Earth. The universe is knowable because it's consistent, and it's consistent because it's governed by fundamental laws that don't change with time or location. Location within the universe might feel special from our perspective, but cosmological principles suggest it isn't. The universe appears roughly the same in all directions, and presumably looks roughly similar from any vantage point. We're not at the center. There is no center to an infinite or unbounded universe. We're simply one location among countless others, all equally valid as observing points. This principle, called the cosmological principle, states that the universe is homogeneous and isotropic on large scales, meaning it has no preferred locations and no preferred directions. Observations support this principle. The cosmic microwave background looks nearly identical in all directions. Galaxy surveys show similar large-scale structure wherever we look. The universe's expansion rate appears the same regardless of which direction we measure. We live in a democracy of locations where no place is special. Earth is our home and are precious to us, but from a cosmic perspective, it's one planet among billions, orbiting one star among hundreds of billions. in one galaxy among hundreds of billions. We're part of the universe, not separate from it, sharing the same nature and following the same rules as everything else. Everything else in the universe shares a common origin in the hot, dense state from which the cosmos emerged. Every particle, every photon, every bit of matter and energy traces back to that initial state. We're all siblings in a sense, formed from the same primordial material, evolved through the same cosmic processes. The iron in your blood was forged in a dying star. The oxygen you breathe was created by fusion in stellar cores. The calcium in your bones, the carbon in your cells, the hydrogen in your water, all of it came from the same cosmic processes that built stars and galaxies. We're not separate from the universe, looking at it from outside. We're part of it, made of it, connected to it through the most literal and physical relationships possible. Looking at the night sky, we're seeing our origins, the furnaces where our constituent atoms were made, the processes that led eventually to planets and life and consciousness. The universe is not just our environment, it's our heritage, our family tree extending back nearly 14 billion years to the beginning of time itself. Time itself might not have existed before the beginning, or the question might not even make sense. If time and space emerge together with the universe, then asking what happened before the beginning is like asking what's north of the North Pole. The question assumes time existed beforehand, which may not be true. We're constrained by language and intuition, shaped by living in a universe where time flows in one direction and where every event has a preceding cause. But the universe's origin might not fit those patterns. It might simply be the boundary of space-time, the edge beyond which the concepts of before and after don't apply. Or there might be something beyond, perhaps other universes in a multiverse, perhaps cycles of expansion and contraction, perhaps something we can't yet conceive. These are deep questions at the intersection of physics and philosophy, and we don't yet have definitive answers. But not knowing doesn't prevent us from understanding the universe's evolution from shortly after the beginning to the present. We can trace cosmic history forward from an early hot, dense state without needing to know what came before or why the universe exists at all. Existence itself is perhaps the deepest mystery. Why does anything exist rather than nothing? Why these particular laws of physics rather than others? Why a universe capable of containing complex structures like galaxies, stars, planets, and life? These questions might not have answers within science. They might be questions for philosophy, or perhaps questions without answers at all. But they don't diminish the wonder and beauty of what does exist. The universe is here, vast and ancient and intricate, following comprehensible laws, containing structure and pattern and meaning, at least to those of us capable of perceiving it. We're fortunate to live in an era where we can observe the cosmos in unprecedented detail, where we can understand its history and structure and dynamics, where we can place ourselves within the grand scheme of things. The night sky that inspired our ancestors with wonder inspires us still, but now with understanding added to the awe. We know what the stars are, how far away they lie, how they formed, and how they'll die. We know the universe is expanding, carrying galaxies away from us. But we remain connected to all of it through shared history and physical law. We are the universe becoming aware of itself, consciousness emerging from matter to contemplate its own origins and nature. So, wherever you are, allow your mind to rest. Let your breath slow. Let your thoughts grow soft at the edges, like starlight diffusing through evening mist. The cosmos will continue its patient work, stars burning through their fuel over billions of years, galaxies drifting through the darkness, space itself expanding at its measured pace. The journey doesn't end. It simply pauses here, in this quiet moment, as you settle into rest. The universe has been unfolding for nearly 14 billion years, and it will continue for billions more, following the same elegant laws that have governed it since the beginning. You're part of that story, made of atoms forged in ancient stars, breathing oxygen created by stellar fusion, thinking thoughts made possible by the chemistry of carbon. Tomorrow, the sun will rise again, as it has for 4.5 billion years. The planets will continue their orbits. The Milky Way will rotate slowly around its center, and you'll wake to be part of it all again, connected to the cosmos through the most fundamental bonds of physics and chemistry. For now, let the universe carry on without your attention. It knows what it's doing. It's been at this for a very long time. Sleep well, and thank you for exploring the cosmos with us tonight.